Cosmologists can trace the evolution of our universe back 13.8 billion years to the Big Bang. But the Big Bang itself is an event still shrouded in mystery. While cosmologists may disagree as to the true nature of the Big Bang, what they do tend to agree on is that when the entire observable universe is far smaller than an atom, the strange world of quantum mechanics surely becomes relevant. From why is there an arrow of time? Or is there a multiverse? And how do we resolve the Big Bang singularity itself? The initial singularity theorems developed in the 1920s had the unreasonable assumption that the universe was perfectly symmetrical. When quantum theory is applied to black holes, it causes them to evaporate, giving off what is now known as Hawking radiation. In the singularity, the Big Bang is a moment of infinite density and curvature. But in the no-boundary state, there's a smooth surface, which, although finite, does not have a single point of origin. The no-boundary proposal treats the universe quantum mechanically, and therefore the mathematics needed to describe this strange quantum world will be needed for the universe as a whole. A path integral assigns a weighting, or relative probabilities, to different possible histories of the universe. The no-boundary proposal is a selection principle that selects the subset of histories of the universe that close off in the past, and so allows us to determine which histories of the universe have the most significant contribution. To describe the wave function and its superposition, physicists use imaginary numbers. But what are these imaginary numbers, and why are they so important for the no-boundary proposal? Inflation is a period of incredibly rapid cosmic expansion, believed to have occurred in the early universe. Inflation is thought to solve a number of problems with standard Big Bang cosmology, and it's driven by a form of matter known as a false vacuum, which causes the expansion to accelerate instead of slowing it down. When this form of matter decays, inflation ends, creating a hot soup of particles. Inflation is generically eternal. In other words, almost all models of inflation lead to a multiverse. A number of scientists have claimed that many features of the universe are delicately fine-tuned. One example is the initial conditions for inflation. In 1998, scientists discovered the universe is accelerating in its expansion, perhaps being driven by a repulsive gravity term invented by Einstein known as the cosmological constant. This, too, has been claimed as a case of delicate fine-tuning. Calculating probabilities in an infinite multiverse is no easy task. It requires a counting procedure known in mathematics as a measure. But there's no agreement among physicists as to what measure to choose. Is there another way out of this measure problem? Critics of the multiverse have said that as other bubble universes are not observable, the multiverse is not science. The second law of thermodynamics tells us that a random fluctuation of something very ordered is incredibly unlikely, but it isn't impossible. Ludwig Boltzmann, one of the fathers of thermodynamics, wondered if our entire universe might be just such a rare fluctuation. The problem is, a brain would seem more likely to fluctuate than an entire universe. So some have argued that these Boltzmann brains would dominate the multiverse and hence disprove its existence. All theories are approximations. In order to move from interesting proposal to something widely accepted, a theory must be precise enough to allow for unambiguous predictions. So what must quantum cosmologists do to achieve this? The aurora borealis is caused by electrons in the upper atmosphere being excited to higher energy levels. As they fall back down to their lowest energy level, known as the ground state, they give off light. This notion of a ground state is helpful to understanding how the no-boundary proposal explains many mysteries of physics. The no-boundary proposal is not really a universe with a beginning, because the beginning only occurs in imaginary time. In real time, the no-boundary proposal implies a universe that is eternal to the past and future. Many models for the early universe, whether they be derived from string theory, loop quantum gravity, or inflationary cosmology, seem to be converging on the idea that our expanding universe has a mirror image of itself, creating an hourglass-like structure for the cosmos, where space and time tunnel into existence from a state of no space and time, similar to the way that virtual particles fluctuate from the vacuum. He claims this has a number of advantages over the no-boundary state. The no-boundary proposal is a theory of cosmology developed before modern quantum gravity theories like string theory or loop quantum gravity were formulated. Multiverse implied by the no-boundary proposal and inflationary cosmology may seem like a modern idea,